Thank you very much, Yukota Sensei, for the introduction. My name is Mohammed Wahib. I am a team leader in RIKIN Center for Computational Science. And again, my talk today will be about Fugaku and how it's pushing forward to enable AI for science and beyond. So first, before I start, I have a prelude or some remark. It's very important to state that AI and machine learning is not magic. And I am sure everybody's noticing there's a lot of hype, let's say, about the capabilities of AI and machine learning. So it's very important, especially when you speak on the use of AI in HPC, to distinguish the hype from the real prospect. That being said, again, there is really a true prospect in AI and machine learning in HPC. And the way we see it is that it works both ways, is that HPC best practices can be used in optimizing and scaling AI. And I will explain in later slides some efforts towards that direction. And it's getting increasingly important since AI workloads are becoming a big part of workloads on Fugaku, and I guess for all HPC centers. And there's also the other way around, which the advancements in AI methods give a very good opportunity to improve and automate scientific simulations in HPC. So again, there's a lot of prospect when we look at it from this way. A little bit about Fugaku, and I think most people here are probably heard about Fugaku and are familiar with it. It's currently the world's second fastest supercomputer, and it is the fastest in Japan. It's in Kobe, where it's operated and managed by RIKIN RCCS in the beautiful city of Kobe. And physically, it replaced the supercomputer before, K computer. And it's a large infrastructure. If you ever have the chance to visit and get a tour, you realize how large it is. And it needs a small powering plant next to it because, of course, it requires a lot of power to use it. And a little bit about Fugaku, it's made up of about 432 racks to be specific. And it's powered mainly by a CPU. There is no GPU accelerators in this system. And that CPU is made up based on ARM ISA. And the name of it is A64FX, and it's basically developed by Fujitsu to be based on the ARM instruction set with something called SVE, Scalable Vector Instructions, which allows us to have let's say, a high-performance version of ARM processors that previous to Fugaku were limited more to embedded devices and smaller CPUs. Per node level, you have a CPU that's very capable. It has 48 user cores plus 4 OS cores, and it has high bandwidth memory to be able to feed this massive compute power of a total of 32 gigabytes. And there's some highlights about what Fugaku was able to achieve in the last fiscal year, and there's stuff also in this year. But those are just highlights that it achieved the first 5 titles, as they call them, in benchmarking supercomputers. Top 500, HPCG, which is conjugate gradient tests, more the performance, which looks to real workloads that are memory bound. HPL AI, which is a variant of high performance impact, but for lower precision, and Graph 500. And that was really an achievement for a system that does not is not based on GPUs and accelerators. It also, research done on Fugaku has allowed us to, as a center, to achieve, it's a big achievement to get the Gordon Bell Award, which was a special version for fighting COVID-19. There's a lot of first principle simulations to visualize and understand how droplets and aerosols are affecting infection. And there's, of course, a lot of research that in the next few slides I will cover, and I'll highlight some of them, data assimilating research, and how it's really effective in improving our understanding of climate and weather, in addition to other areas of science, like understanding protein analysis software. And with that, I actually will talk a little bit more on AI and Fugaku. So again, as of June 2022, it's the second fastest computer in the world. It's still fastest on HPCG and Graph 500, which look more like real workloads than high-performance Linpack. It uses a64FX ARM processor, as we mentioned, with 32 gigabytes of high bandwidth memory. And actually, a big challenge, you have to keep in mind that Fugaku plans started around 2013 or so. And that was not yet a time when AI and machine workloads were big in the picture. So it was designed without taking AI and machine learning into consideration as a main workload, right? So that meant after Fugaku was delivered, a lot of effort went into qualifying or building actually the ecosystem for Fugaku to allow for deep learning in specific and machine learning in a more general way. And that actually shows the strong design points of Fugaku, even though it was not designed for those workloads that have their own features that may be different from other HPC workloads. And nonetheless, when building the ecosystem, it allowed it to adapt to this kind of workload. And it's not a finished task, it's an ongoing task because there's still more and more parts to fill to work with more and more larger models like transformers and such. So again, it has been an ongoing effort and between Fujitsu and Riken and also outside collaborators to build and improve the ecosystem to be more and more useful for scientists who want to use Fugaku. One point before I move to real applications, I'll talk a little bit about scaling AI and machine learning. There has been past an ongoing effort to see how Fugaku does on benchmarks that matter a lot to track the capability of systems, CPUs or GPUs that can host these kind of machine learning workloads. The most common one, or let's say it's like the high performance impact of machine learning performance, is called MLPerf. And there's a subcategory of it called MLPerf training HPC, which selects specific machine learning 3 exactly benchmarks that reflect more the requirements of HPC to emphasize, for instance, the stress on the I/O and storage system in some of these simulations might be, which looks, again, more closer to how you would use machine learning HPC applications and not the typical applications like image classification or language models. And we have had the paper published in SC, one of our SC workshops last year that involved a lot of systems from different countries, like PaceDyn from Europe, Cori systems in the US, Frontier, and ABCI also in Japan. And what's interesting in that all of these systems essentially, except for Fugaku, are using GPUs. Maybe Cori Knights Landing is using it as an accelerator. So it would be interesting to see that a CPU design machine that was not even designed for these machine learning workloads to be able to perform that well and get decent performance on the MLPerf HPC benchmark, which encourages us to more and more improve our ecosystem to go after improving the performance on those benchmarks and actually future benchmarks. So this was a long effort and still ongoing effort by Riken and Fujitsu jointly working and also with external collaborators to make scaling of AI and machine learning on Fugaku much more robust and also stable and also usable, which is what we care about in the end. We don't just submit benchmarks to appear on a list. The main focus behind that is to build the ecosystem to allow us then to simplify the task of scientists and engineers who would want to use Fugaku. Now I will, from now on, have the remaining time dedicated into 2 parts. One is where I speak in general about AI for science on Fugaku, which is effort by Riken RCCS research teams and priority applications, and essentially success stories on Fugaku, which is not work of my own or my group. In the end, I will focus a little bit on work happening in my group. Again, I'm speaking on behalf of the people I show their slides. I maybe even don't understand a lot of the science behind their work, but this is more like to give the audience today an understanding of the breadth and the depths of how Fugaku is contributing into scientific domains that are increasingly relying on AI. There's actually a book chapter we assembled that summarized the next few slides called The First Exascale Supercomputer Accelerating AI Science and Beyond, which is actually the title of the talk today. And I would like just to thank also specifically Kento Sato, who's a team leader in Riken RCCS. He helped a lot in collecting the next few slides. So I will, it's essentially from now, it's just one slide per project to just show that this is already work done and published to just again, give the audience an idea about the breadth and the depths of how Fugaku is impacting research that relies on AI, and also to motivate the audience to think if this would motivate them to also themselves try to look in their applications and their simulation and see if they can also try and want to explore the prospect of using machine learning and AI. Again, it can sometimes improve or can sometimes automate some of the tasks. So this first work was from the RCCS teams, from Tsubukura-san's team. And for each of those, in the bottom of the slide, you will find the paper that discusses the details. I'm just giving a very high-level introduction of each one of them, very brief. So this one, for example, looked at the composition of modes in flow fields, which is an important task, especially in 3D, because it's really computationally intense when you would want to do this decomposition. And historically, it has been done with some heuristics, but it's really time consuming. So what the researcher did, Tsubukura team, in this thing, that they had 3D flow field snapshots. So it's a 3D problem, and they had a convolutional neural network. The issue with that, though, is that this is very compute intense, that this is a 3D problem to store the activation of this model. And for that, that was actually an impressive scale, because training required that not only data parallelism would just split the data on different nodes, but the model stored itself it requires a lot of memory. They have to also do model parallelism. So it combines two types of parallelism: model parallelism, in which they split the model into different nodes, and data parallelism, at which the input data is also split. And this went to learn or train it for up to 1K, 10K actually nodes on Fugaku. And again, the results were really impressive when they had the full order model to the ground truths and compared to the output of neural network. The result was quite impressive in this case. And I think it will be increasingly used in this area as software stack gets more and more mature. Second example, this is a work from Imamura team in Tohoku University. This was a priority application, which is one of the applications pre-selected to be a priority application for Fugaku. And as the name implies, it's a priority application of importance. This was looking into tsunami simulations specifically, in which you have as an input your tsunami waveforms on offshore area, and what you want to see is what is the flooding conditions in coastal areas. So after a tsunami hits, there's always expectation there would be flooding. And it's very important to understand these floodings, because based on it, you can mobilize rescue teams, and also make decision makers would be empowered by knowledge on what to expect the flooding would look like, and accordingly do plans for emergency and designing cities based on it. So the AI model is essentially predicting the flooding condition in coastal areas, again, after waveformat on offshore, which you would imagine is an important thing you would want to have when you study the effects of tsunami. And they did a lot of work to train the data that's generated on Fugaku, and then they would be able to train that. And they wanted also real-time prediction, because it can be the case that these events happen without knowing ahead of time, usually. So you'd want not only to study it offline to understand more about the effect of the flooding, but also be capable to do it in real time, because this is prediction at the time of disaster, which is valuable. And as you can see, the assumed flooding here, which is a model that's created, which you can consider the ground truth in this case. And this is an example of the AI prediction showing the flooding and the depths, which can go up to 2.5 meters. And as you can even visually see, it's a very reasonable quality of prediction that's much faster than if you would do it in other methods. And as usual, the paper is down there if you would want to understand more about the details, or contact the authors in Imamura's group in Tohoku University. Next one was again, another priority application. And this was a joint effort between Fujitsu and other affiliated labs. And the main focus is they want to understand the mechanism of how certain cancers become drug resistant. It was really unclear, because you have to understand essentially the genes. You have to determine the genes that cause the resistance to the drugs. In this specific case, he chose lung cancer. to study it. Again, methods that are existing methods in the literature actually are very time-consuming. And also, they don't reveal a lot of details in finding the patterns, in finding the genes that are responsible for this exact resistance to the drug. So it was imperative for them to understand it. And as usual, a lot of effort went into data engineering and preparing the data sets. And this is a recurring theme in this area of using AI in simulations, that creating or gaining or having a data set is a very important point. And again, they had very good findings that were important in that area, which I think is very encouraging for people working for AI and drug design. And there is a big project, actually, a unit working in AI and drug design in REEC and CCS, that they have very ambitious goals towards applying it in different levels of research, because this is a very open area with a lot of prospect. The next example, which comes from Makino Sensei, who was in REEC and RCCS, now in Kobe. And this was looking at the expansion of supernova shells. And this used deep learning for high resolution simulations. So where you would start from initial conditions. And what happens is there's the data before, which is before the explosion, before the supernova explosion. You have a density distribution. And after the explosion, there's temporal and spatial changes in the density. This is what we want to understand. What's the changes that happen in density, spatially and temporally? And that's why in this case, they combined a very nice combination of two types of machine learning models, CNNs, convolutional neural networks, which are known to be very good in extracting spatial features, and LSTM, which is good in temporal stuff because it tracks temporal dependency in your input. And while training, this can take several days, and this is, again, an expected thing. The training took a long time, but then once you have a model, the inference or the estimation is just a few seconds, which is a very powerful thing in the toolkit of people doing research in that area, since now with this very low time to use, a few seconds, it's very good for people who want to do more and more research in that area to understand the effect of supernova explosions. And again, this minor video shows the ground truth versus prediction. And again, to the error threshold they defined to themselves, it was very acceptable and good. And from my understanding, and even the conclusion of this paper, they wish also to include this model that they made for a simulation environment on Fugaku to be available for users to use it. Now, those were examples that were direct examples worked by REEC and RCCS and the priority application teams that used some form of AI in Fugaku. This is by no means a complete list. It's just a few examples that time would allow. And I would refer you to the book chapter if you want to know more. A little bit more about work which is using AI-based scientific achievements. Fugaku is not used directly per se, but what we think they're important in is that this is not just a work that they achieved and they move on. They still want to improve and build on it. So we aspire that in the future, we would attract further work to base on those achievements to be using Fugaku in the future. And hopefully that means, again, it will extend the base of using AI for science on Fugaku. And the highlights of this work, this is again work by RCCS research teams and priority application programs. So this is work from RCCS, which looked at the flooding and debris. So typically after floods that can come from heavy typhoons or heavy rains, you have debris that flow. And this is a problem because you want to understand the disaster, flooding damage that's happening to estimate it. So you can, again, just like that tsunami work earlier on, understand what you can do. And this work comes from RCS teams. And again, in this work, they started from image analysis of remote sensing imagery collected. And it goes through phases of inference and extracting topographic deformations from that, which they extract by using models like UNets, which are models to segment the image and give you the boundaries of those topographic features. Then you are capable, based on that, to see, okay, if there's flooding, how would the debris flow when it happens? And again, this is an important line of work that is very relevant to Japan, I think, the world at large, considering how the devastating effect of floods look like. And in this figure on the right, the lower one is showing essentially what was achieved by the AI method in tracking the debris. And you can see the very fine-grained details of the flow of the debris versus the ground, like the classical methods or the basic methods that were tested before. So in this case, not only was it fast, but it allowed much more fine-grained control or much more fine-grained results that they can inspect to build their conclusions upon. Another work, which is again, didn't run on Fugaku per se, but as we move to the future, it will be relevant and hopefully it expands also at some point to build on it. You can build on the work to use on Fugaku. So this is looking at images that change over time, right? Type evolution image data means you have images, but through time, there's changes and you want to track. So what do you look at is how do you decompress it by using a deep neural network? So when compressing those frames, because you can think of these images as series of frames, like in a video, for instance, they try to predict future frames from the original base data. So based on some frames, you want to predict the future ones, and then compute the delta values, how much the future frames will change versus the current original base, and then they encode it. And this is how they compress. They just save this base frame and the compressed data that's based on that. So essentially, it competes directly with existing encoding methods. And actually, it appeared much higher compression ratio to existing video encoders. And those are very, very well-established video encoders that are well designed by experts who understand exactly how to do the best encoding possible to these kind of images. And which, again, they used a deep neural network for that, where they started from a trained model and they had original frames, the predicted frames. And then after they have predicted frames in the future, they would look at the deltas, the differences, and this is what they saved as compressed frames. This work came from Riken RCCS, Riken Spring 8 facility, because they have a lot of data like this you would want to compress. You're interested in this application of this, and Florida State University. Another priority application, which looks exactly how to represent classical data in quantum circuits. Classical data can be images, for instance. So think of an image like this. How would you represent it if it would be represented in a quantum circuit, because your application requires that? How would you represent it? So it looked into constructing the optimal circuit for this classical data, at which the quantum state is represented by the amplitude encoding. So essentially, it's an encoding scheme that you would take the source image, encode it in a way. The amplitude encoding itself now can be mapped on a quantum circuit. This, again, method could be very useful as we see there's increasing importance of quantum simulation and quantum computing at large. And handling classical data has always been a question. How will you handle the legacy of data? Because often applications or scientific applications deal with classical data like images or video or time series or text or so on. This, again, was a priority application with work from Riken RCCS and Riken Quantum Computing Center. I will not continue because I mentioned I cannot list all of the efforts that have been done so far that uses AI and big data on Fugaku and also outside Fugaku. There are many works where Fugaku is not used, but they were priority applications and involved Riken RCCS researchers. And we think in the future, more of these, as Fugaku stack becomes more mature for AI machine learning, more of these applications we can jumpstart future direction that are based on those works in the future to support it on Fugaku. And they use, for example, I cannot list, there's a lot of work happening, like gene analysis, for instance, and also machine learning using a neural network for quantum many-body solver, or what they call quantum AI. Another is facilitating ab initio, like configuration of solids, which is increasing. There's a lot of papers in that area. DFT, which is a famous classical, one of the classical workloads you see in HPC centers running and consuming a lot of cycles in systems. And here where they try to use supervised learning, in this case, to reduce some of the cost, and et cetera, and et cetera. There's a lot of work. And again, the book chapter, I would be happy to share once it's published. It's about to be published. I mean, we almost finished. It's just in press, let's say, that summarizes a lot of those efforts. Now I will shift gear a little bit. So far, I spoke to highlight essentially what have been done on Fugaku. with the effort of so many hardworking scientists. And this is just the beginning. I think more yet has happened, but that was more work of a lot of teams in Recon RCCS and outside. And I just highlighted them. Now I'll highlight a little bit on the efforts we do in our team, the high performance AI system research team, in bridging AI and HPC. We do that with emphasis on Fugaku, obviously, because we want Fugaku to have a stack software, mature software stack to enable more scientists to use it. But also a lot of our work generalizes to systems other than Fugaku or future systems. The team involves many scientists and also visiting scientists and visiting students. We are based in the Tokyo office of freaking RCCS. Again, so the important message is, unlike traditional HPC applications, AI workloads have multiple bottlenecks. I'm now speaking about HPC and AI, the part of our work that we look into how to apply best HPC practices in AI. Again, for many HPC applications, you can know the bottleneck, and the bottleneck is probably sustained across generations of different systems. Some applications can usually be memory bound, some can be network bound, some can be IO bound. AI workloads is very different because there's a lot of varieties and flavors of AI workloads, and also the way you configure them is very different. Which data set you use is very different. What type of data set, what type of model? Also, how do you scale? Do you scale in a data parallelism way or a model parallelism? So this can stress different bottlenecks at different levels of the stack. So if you look at different levels of abstraction, you can easily stress all those bottlenecks. You can easily have an issue with memory capacity or memory bandwidth or IO if your data set is pretty large, throughput, latency, for both compute and memory, network, even if you want to really scale at large size, and just pure old compute. And we have tried to contribute in the last 5 years or so on different levels of the stack. Again, I don't have the time to summarize all of the work here or mention all of the work. I'll just summarize and give highlights. If anything interests you, please reach out. We'd be glad to discuss more on it. So for instance, one line of work looked at the problem of parallelism. How would you parallelize? In HPC application, the way to parallelize for established HPC applications are more or less usually known. So if you have, for example, climate or data simulation, the way you decompose a discretized domain is more or less very well understood because it has been done for 30 or 20 years, or maybe 40 years even. Maybe more actually. But these kind of workloads in AI and specifically in training deep neural networks, again, they vary a lot based on what you're stressing. I mean, essentially the balance between the sample size and the number of samples, the model itself, how it looks like, its dimensions, its complexity, right? And also the system used. How does your network look like? Is it a flat system with just CPUs and no GPUs, or does it have GPUs? And et cetera, et cetera. So understanding the level of parallelism in deep learning was an urgent task. So that work, which was in HPDC 21 last year, we took a systematic look into, okay, if we train deep neural network, what are the different ways you can parallelize it? And there's about 1, 2, 3, 4, 5, 6 of them. And there's even, they say, hybrids of these methods. To understand how would you parallelize. At the bottom level, you're just doing a lot of tensor operations. At higher level, though, you would understand how would you decompose those tensor and what would be the bottleneck in every scenario and when would you use each scenario of them. And we propose a oracle in which you can feed it the data set specification, the model, your system, and then it can tell you the best strategy, depending on what you optimize for. Are you optimizing for compute time or communication, or you have a budget for memory per processing element, or do you have a budget on the maximum number of element, like processing elements, nodes you have? You want to pick the most efficient parallelization scheme. And I think this study was important for us, number one, and for others also, to understand more on the limitations of parallelism as we move forward. Another example, which is looked into what they call landscape analysis. So machine learning methods, you have very high dimensional non-convex loss functions usually used. And if you use stochastic gradient descent or any of the methods that rely more on essentially deep neural network, it's essentially fitting loss function. So you would want to understand more about what they call landscape. How does it look like? So in that work, we realized that we need a way where you take those very high dimensional functions, loss function, and be able to visualize and understand them more. And in that work, we looked a lot into methods on how we be able to do that. And I think it was useful for us and other because it improves our understanding. Another example is looking, again, we mentioned there are different bottlenecks. In this one, it was memory capacity. We realized for many workloads, you're just bound by the capacity of your system, be it CPUs or GPUs, which is a big limit because you don't want to add nodes just because you don't have memory. This is very inefficient. So we looked into method that does out-of-core computing, which it does swap in and out of compute. If you have a GPU-based system to the CPU to use it as a way to essentially go out of core and move the data you're not using outside the GPU and make way for the data that is being used and do prefetching in a very synchronized scheme. And with that, we were able to scale, that was ABCI system in Japan with GPUs to thousands of GPUs to scale for many models, which was very important. And actually several production frameworks like DeepSpeed and so on. After that, that was a paper in SC20 pushed in that direction. I will not go through that, but also we have tried to work at this. We tried to look at this work from the angle of network architecture, what's fitting, because it can be a bottleneck. Finally, AI and HPC, which is something also we're looking at recently, which is a recent project we started, how to use AI for auto code generation in scientific programs. There's a lot of effort that has been in compiler technologies in the last 40 years that auto generates codes, but it loses context and also it's constrained because it's slow. I mean, you can't have it a slow compiler. Also, there's also efforts on high-level code transformation, which is good in getting context, but it's very problem specific. For example, people doing code to optimize for cache blocking for specific codes. And there's auto-tuning, which we know is scalable, but doesn't generate code. It just picks from existing code. So in this work, we try to apply AI or build on the achievements of AI, or recent achievements to improve HPC codes in this intersection, which intersects like compiler technologies, which can generate code with high-level transformation, can express to improve the locality of the code in an auto-tuning way, which is very scalable. And this is, again, a recent project that we started, and I think we're pretty ambitious about it. With that, I want to say that Fugaku is driving innovation in bridging HPC and AI, and I think it will continue to do. We're just starting. The software stack is maturing every day, day after day, and I think we will see more and more good outcome out of it. And with that, I would like to thank you, and sorry if I stepped over time.